Okay, we've looked at the Fourier series as an infinite sum of complex sinusoids, but many of the functions that we're going to deal with will be real valued. So it's of interest to consider writing out the Fourier series using only real valued sinusoids. For this, we need to note that if f of t is real valued, then by definition, as we noted earlier, the coefficient c sub n in the Fourier series will be the complex conjugate of the coefficient c sub minus n. So if we look at the sum of the two terms corresponding to these two coefficients, we find that we can express that sum in terms of real valued sinusoids. So let's take the sum c sub n times the complex valued sinusoid that it multiplies, namely e to the j 2 pi n over big T times little t, plus c sub minus n times e to the minus j 2 pi n over big T little t. Excuse me. So again, c sub minus n is just the complex conjugate of c sub n. So here we're just adding together two complex conjugates. So what we'll get will be twice the real value of either one of them. So let's say twice the real value of c sub n e to the j 2 pi. Now we can express c sub n in polar form, so this will be twice the real value of the modulus of c sub n times e to the power j times 2 pi n over big T times little t plus the angle of c sub n. We can now apply the Euler identity. And this gives us twice, well, let's in a single step apply the Euler identity and take the real part. So we'll get twice the modulus of c sub n times the cosine of 2 pi n over big T little t plus the angle of c sub n. And then we can apply a double angle formula to rewrite this as twice the modulus of c sub n times the cosine of 2 pi n over big T times little t times the cosine of the angle of c sub n. Excuse me, minus the sine of 2 pi n over big T little t times the sine of the angle of c sub n. Well, here we're taking, in the first term, for instance, we're taking the modulus of c sub n and multiplying it by the cosine of the angle of c sub n. That will just give us the real part of c sub n. So we'll get twice the real part of c sub n times the cosine of 2 pi n over big T little t. And then in the case of the second term, we're taking the modulus of c sub n and multiplying it by the sine of the angle of c sub n. That will give us the imaginary part. So we get minus the imaginary part of c sub n times the sine of 2 pi n over big T little t. So here we have a sum or a difference, if you like, of a real valued sinusoids. First is a cosine, the second a sine. So we can write this as a sub n cos 2 pi n over big T times little t plus b sub n times the sine of 2 pi n over big T little t. And this is going to be a sum of two terms in our new version of the Fourier series that's expressed exclusively in terms of real valued sinusoids. So in this case, we'll use a coefficient a sub n for the cosine terms, and it's going to have the value of twice the real value of c sub n. And b sub n, the coefficient of the sinusoidal term, will be minus 2 times the imaginary part of c sub n. Of course, we can write out formulas for computing a sub n and b sub n directly. And if we do so, we find that a sub n is 2 over capital T times the integral from minus t over 2 to t over 2 of f of t cosine 2 pi n over capital T little t dt, and b sub n is 2 over capital T times the integral from minus t over 2 to t over 2 of f of t sine 2 pi n over big T times little t dt. So we can compute a sub n and b sub n directly in this way. And then we can rewrite our Fourier series, which we've been writing as a sum from n equals minus infinity to infinity of c sub n e to the j 2 pi little n over big T little t, as a sum. Well, we'll take the case n equals 0, make the case n equals 0 a separate case. For n equals 0, of course, we'll find that the b coefficient is 0. If n equals 0, then this sign will give us 0. So b sub 0 is always going to be 0. So in the case n equals 0, we'll just have, in general, an a sub 0. And then we'll simply take the sum n equals 1 to infinity of a sub n cos 2 pi n over big T little t, plus the sum from n equals 1 to infinity of b sub n sine 2 pi n over big T little t. Of course, we only sum over non-negative values of n because we got this expression a sub n cos 2 pi n over t plus b sub n sine 2 pi n over t as the sum of the two terms corresponding to plus and minus n. So we're only summing over non-negative values of n to get our Fourier series expressed in terms of real valued sinusoids. So this is a common form for the Fourier series. Obviously, it applies whenever you're dealing with a real valued function. Students sometimes seem to find this Fourier series easier to work with, somehow more understandable. But the complex form is very convenient for theoretical purposes. Okay, we're going to be talking now about convergence of the series, about how good an approximation you get by using a Fourier series, if you like, to represent a periodic function. And in order to do that, we're going to talk a bit about the power in various terms. of our Fourier series and the power in the function f itself. We've talked a bit about this before and explaining why we were using decibels to represent the magnitude curve of the Bode plot. In particular, we applied a sort of convention that says that the power in a signal is proportional generally to the square of its amplitude. We can then talk about the average power over a period. We get that average power by first of all finding the energy over a full period, which would be the integral of the power over that period. So this would represent the energy, if you like. And then we divide that by the length of the period. So the average power in a periodic function f would be given by this expression. Now we've just talked about bringing in real valued sinusoids, so let's see what the average power in a real sinusoidal signal is. Okay, well, we know that the power gain in a sinusoid, say, sine 2 pi n over capital T, the average power will be the square of that sinusoid. Okay. So, how are we going to find, the power would be that expression, so we'd have to average it out over a period. So how do we deal with the sine squared term? For that, it's convenient to bring in double angle formulas. So using double angle formulas, which you can easily derive if you don't have them memorized, you can derive them using the Euler identity. So you can show that sine theta sine phi is cos theta minus phi minus cos theta plus phi divided by 2. Now we're looking at the case where theta and phi are equal, namely theta and phi are both this angular frequency multiplied by little t. So what does this formula give us in that case? If we take the cosine of the difference between the two angles, when the two angles are equal, that just gives us 1. And then the second cosine term in the above line will give us cosine of twice our angular frequency times t. So we'll get 4 pi n over capital T. Now, this cosine, therefore, has twice the angular frequency, and therefore half the period of our original sinusoid. So if we integrate over one period of the original sinusoid, that means we're integrating over 2 periods of this cosine. We integrate a cosine over 2 periods, it's going to give us 0. So the average value is going to work out to be 1/2. We integrate this over an interval of length t. This cosine will give us nothing because that's an integer number of periods of the cosine. This will give us 1/2 t, but then we divide by t, so we get 1/2. And that is the average power in a sinusoid of amplitude 1. And obviously the same applies if we use a cosine instead of a sine. So, what does this say about the powers of the terms in our Fourier series? Obviously, for the real form, we're going to get, for the power of any term, it's going to be 1/2 times the magnitude of its coefficient, times the absolute value of its coefficient. What about the complex exponential terms, or complex sinusoids? Suppose we compute the average power of one of our terms in our complex sinusoidal Fourier series. So we want to take the integral of the square of the modulus of this complex sinusoid over one period and divide it by the length of the period. Well, the square of the modulus can be obtained by taking the complex sinusoid and multiplying it by its complex conjugate. So we take the complex conjugate of c sub n and multiply by e to the minus j 2 pi n over capital T, little t dt. Now, these two exponentials are simply going to cancel each other out. Those are inverses of each other. So we're just going to end up with the integral from minus t over 2 to t over 2 of c sub n times c sub n star dt. And that will just give us the modulus of c sub n squared. So, whereas if this sinusoid, this real sinusoid that we had considered earlier, had been multiplied by a coefficient b sub n, we would have had a b sub n in this integral, so we would have ended up with an average power of 1/2 b sub n squared. In the case of the complex sinusoid, in the original form of our Fourier series, we don't get the factor of 1/2. We just get the modulus of the coefficient itself squared. So there's a factor of 1/2 that enters in when we're using the real valued sinusoids. So what we're going to do next, and I think we'll wait till we get another video, is to compare the power the average power of f of t itself with those of the terms in its Fourier series. We're going to see that, as one might hope, the average power in f of t is equal to the average power in the entire Fourier series. But we'll also see essentially that the powers in the various terms in the Fourier series are additive. So the power in f of t is equal to the sum of the powers in the respective terms of the Fourier series. That will give us one way of measuring how quickly the Fourier series is converging toward f of t and how good an approximation of f of t the Fourier series is giving. So we'll look at that in the next video.